Good afternoon. Welcome to this introductory class in physics practicals. In this class, I want to talk about four or five major items. Number one, why practicals in physics. Number two, what are the major components of practical physics? Number three, how do we present our results when you perform experiments? Number four, how do you handle error while you are performing the experiment? And number five, deductions, conclusions, and inferences. Now, why practicals in physics? Physics, as you know, is a science course. And as a science course, in science, the way we study science is by experimenting. So we perform experiments in physics. And your experiments in physics are meant to achieve something, is to verify. We use experiment to verify theories, hypotheses, and laws. Hypotheses, theories, and laws, they are postulations made by scientists or researchers which has to be verified. So we come to the laboratory to make verifications of those hypotheses, theories, and laws. So basically that's why experiments or practicals are necessary in physics. Now, what are the major components of practical physics? Number one, like I said, what you come to do when you are performing an experiment is to verify a law, an hypothesis, or a theory. So when you want to come to the lab, there must be a theoretical basis for what you want to do. You have a theory you want to verify. That's number one. Number two, you must have a set of apparatus, what we call apparatus. These are the equipment or the components, the instruments you are going to use. So, when you come to the laboratory, you will be given some set of apparatus based on the equipment, the theoretical basis on which they want you to perform experiment. Then secondly, you must have a set of instructions, or what we call procedure. The procedures are the step-by-step stages or actions you must perform in arranging the equipment or apparatus such that you will be able to achieve your aim. Okay, so it means that when you come to perform the experiment, there must be an aim. The combination of the apparatus will help you to achieve that aim, and when you take measurements. So in physics, most of the procedure, after you have been able to set your apparatus correctly, most of the other things you do is to take measurements. Like we take measurement of length, measurement of time, measurement of weight and masses, etc. Okay, so after that, you go to the presentation of your results. Your results must be presented in such a way that you can make inferences or conclusions. You can draw conclusions, based on your observations that you made in the observations and measurements that you made during the course of the experiment. Okay, so the next thing now is the presentation of experimental results. In presenting your result, there's a format you must have to follow. The format are, number one, the title of the experiment. The experiment must have a title. Number two, the aim that you intend to achieve. Okay, the aim you intend to achieve on performing the experiment. For instance, let's take the example of simple pendulum. You are performing an experiment on simple pendulum. The theoretical basis of simple pendulum experiment is the simple harmonic motion. So, what is our aim when we come to the aim? An aim may be such, example, determination of the acceleration due to gravity. That's an aim. Okay, and the title of the experiment will be simple pendulum, but the aim will be determination of acceleration to gravity. So there must always be an aim. After that, there must be the procedure. Like I said, most of the experiments you'll be performing in the laboratory at this level, we have supplied you with the procedure. So every experiment has its procedure. You may not necessarily reproduce the procedure, but you can draw when necessary. You can draw diagrams to show the procedure you have taken. After that, you present your results. In presentation of results, in your result presentation, the result can be presented in 2 or 3 ways. Number one, we can ask you to tabulate. Most of the time we tabulate, that is, all the measurements we take, we put them in table. When you are tabulating, you must tabulate in such a way that your tabulation is, your table is a straight table, not cut or segmented. So that's what we call a composite table. All right. Then we can also, in some cases, you may not even have to have a table. There are some experiments, especially in optics, where we just take measurements, then we take average. But in some cases, you may have to do table. Then when you do table, most likely they may ask you to plot graphs, graphical representation of your measurements, which will help you to make some other deductions. So our presentation may be in form of, just writing the results. Number 2, presentation up in a table, and then number 3, graphical representation. Okay, so now one thing we must have to talk about is, let us look at the example here. I want to take the example of simple pendulum experiment. In simple pendulum experiments, like I said, our aim is to what? Is to determine the G, that is acceleration due to gravity. Acceleration due to gravity is our major. So now, but this equation is the equation that gives us the period of the simple pendulum, the period of oscillation of the simple pendulum. Now, this equation, as you look at it, is not a straight line equation, because this is T equals 2 pi root L over G. Now, most of the time at this level, when we have equation like this, it is required of you that you do what? You linearize the equation. That is, you make the equation to become a straight line equation that can be plotted in a straight line, like forming y equals mx plus c. Okay, so we may have, most of the time, we may have to linearize your equations to match up to a straight line graph. So, in some cases, when you are having an equation like this, y equals to x raised power n, you see, you may have to, in order to linearize, you take log of both sides. When you take the log, you have log y equals to n log x. N log x. Where log y now serves as a what? Your y-axis. Log, n equals to the slope. Log x. This is supposed to be x. Log x now is your x-axis. And then you have your intercept. In this case, there is no intercept in this equation, so intercept is equal to 0. Now let's go back to our equation here, our simple pendulum equation. T equals to 2 pi root L over G. How do I linearize this equation? I can simply take the square of both sides. If I square both sides of this equation, I get this equation. This equation, it gives me T squared equals to 4 pi squared over G times L. Now, I've tried to put this in bracket because this is a constant. This is what I'm looking for. This is a constant value. Now, in the simple pendulum experiment, I'm expected to measure the time of the time or period of oscillation and then plot it against the length of the pendulum, meaning that there are two variables. The dependent variable, which is what? Which is y, or let us say t, is the period, and the independent variable, which is L, which is the length of the what? Of the pendulum. So I can now put it into y equals to mx. So this has been linearized now. This equation is a linearized form of the original equation that is given. Alright, so the setup or the procedural setup for the experiment looks like this. This is a ritter stand. This is a pendulum suspended with the head of a split cork and clamp. And then you have a ruler that you use to measure the length, and then you have your stopwatch that you can use to measure the time. So when you do this experiment, you are expected to take the time. Now, you will be asked to tabulate your result. You can tabulate your result such that you have L, you have T, you have, and then you can calculate T squared. So when you calculate T squared, the next thing for you to do is to present your result graphically. So in presenting your result graphically, there are some points you have to take note of. Number one is the selection of your scale. Your scale must be selected in such a way that your graph covers a greater part, at least 3/4 of the page of the graph. So, units of scale must be selected such a way that it gives enough room to cover the space, either on the y-axis or on the x-axis. That's very important. Number two is that having been able to select your scale correctly, you have to take note of the fact that you don't fix points in your graph. You have to avoid a situation whereby, assuming you have in your x, maybe your value x is 40, and then your value y is 0.2. Now say, okay, this is 0.2, 0.4, 0.6, 0.8. Now, because this one is 40, I just fix it to 40. Because this one is 50, I just no. In plotting your graph, you have to trace the true values. Your scale must not necessarily be equal to exactly what you have in your table. That's what I'm saying. So you have to take note of that, so that your scale does not necessarily follow what you have in your table. Your scale must be such that it is well spaced enough and you can read in between values. Alright, so when you do this kind of experiment, this simple pendulum experiment, we are likely to have a graph like this. This is T axis, this is T squared axis, and this is the L axis. Alright, so we plot the graph. This is the straight line graph passing through the origin according to this equation. Y equals to mx. Alright, so you plot your graph perfectly. In plotting your graph, there is also T. This T squared, I believe you know that it is obtained from our time. You take time, for instance, when you are performing this experiment, you take time for 10 oscillations. The time for 10 oscillation, okay, we now find the period. The period of oscillation is now that time divided by 10. Now I'm still coming back to that. I'll still do some explanation on error handling. Now, so our graph is going to be something like this. This is what we call line of best fit. A line of best fit, when you draw graphs, if you have about 7 points, at least 3 of those lines, 3 of those points must fall on a straight line. Those ones that fall on the straight line, the perfect, or what we call line of best fit, is a line that passes through equal number that leaves equal number of line and the points on either side. Like here now, you see that I have the point here, left hand. I have the point here, left hand. I have the point left hand here. It may not necessarily be, because it may not necessarily be the same number on this side, the same number on this side, but it's passing through as many as possible points on the straight line. Alright, so that's line of best fit. So this is your graph. And then from there you can find your slope. Your slope also must be found or must be located in such a way that it covers a greater part of the graph and not necessarily on the points on the graph, so that you don't repeat your mistake or your error. Right? So if you have plotted a straight line, you can take a point here, the lowest point here, and take the highest point here that I have in my own case here. So this is my y2, this is my y1, this is my x1, this is my x2. I can find my slope. Slope is equal to delta y over delta x. Alright. So with that you can find a slope, of course, you know that. But now, another thing which you have to take note of is error handling. There are 2 or 3 ways by which we handle error when we are performing an experiment, especially when you have to draw graphs. If you don't have to draw graphs, you know, one way of avoiding or minimizing your error, because it is not possible to perform experiment without having errors. There are different categories of error. We have random error, we have systematic error, we have, environmental error due to environmental circumstances and so on. So one of the ways of handling error is to repeat your measurements. What do I say? Repeat your measurements. So like this T now, if I take time for time oscillation here, I can take it T1, T2, or T3. So that I have series of T's, T1, T2. And so that means I'll be able to take my time twice at least, and I can find average. By so doing, minimizing my error. Another way of handling error is what I have here on this graph. This is what we call error in slope. Now, what do I have here? I have 2 parallel lines to my main line, which I call the line of best fit here. These parallel lines are, number 1, the one up and the one down. You will discover that the one up is passing parallel to, is passing through the points on this side, parallel to the line of best fit, while the other one is passing parallel to the line of best fit on the other side and across those points. These are what we call error lines, and these error lines we use the error line to determine the error in our slope. How do we do that? We first of all take what we call vertical displacement of the error lines. The vertical difference between the error line, I call it omega. Alright? Okay. Then the range, that is the horizontal difference. This is taken along the first point that is plotted and the last point. Okay? We call that one range error. Range, but horizontal range. So when you've done that, your error in slope now is given as this. As 4 omega over nr. 4 omega over nr. That's my error in slope. So, having taken the value of omega here, the distance between the point, this is the point of the upper arrow line and the lower arrow line. That is omega. I multiply by 4. This is my range. And then n, what is n? N is the number of points that I plotted. Like in this case now, how many points did I plot? This is 1, 2, 3, 4, 5, 6. I think n is 6 or thereabout. So that is the number of points that I plotted. With that, you can find your error and slope. When you find your error and slope, now that error and slope must be added to the error in this way, so that the true value of my slope, assuming my slope from the line of best fit is given as x in the units, okay, my true value now will now be what? Will be if the slope, I mean the error in slope is, let's say the error in slope is x prime. Error in slope is s prime, so that by the time I calculate this, I got s prime. By the time I calculate this, I got x. The true value of slope will now be x plus or minus x prime. That gives me the range of my error. Means that my error is plus or minus x prime. So I can use that to find my slope. So the true value of my slope will be something like this. Assuming that x prime is 0.01. It means that my slope is 5, the range of my slope is between 5 minus 0.01 and 5 plus 0.01. Okay, so having obtained that this is my slope. Remember that my slope is not actually what I'm looking for. I'm using my slope to make deduction. I want to deduce the value of g. So I must get my slope here. After getting the true value of slope, therefore I can find g. So my g now will be given from this. The true value of g ranges between this value. Okay. Error in slope. Okay. Alright, so you can also write, you discover that if you look at this, if you want to have something to remember, you can write it as error in slope over slope, that is slope, the value of your slope is equal to error in g over g. So with that, if you want to find actual error in g, you can obtain actual error in g. So that error in g will be, of course, you can make that subject of the formula. Error in slope times g over slope. Alright, so this is how we undo our errors. We undo error by taking our readings more than once. We undo error by drawing our error lines against our line of best fit, and then from there we can calculate our error slope. Okay, so now the last point here is making deductions. Actually, the deduction or inference we want to make from this type of experiment, for instance, is deductions made from the slope and the intercept. In this case, we don't have any intercepts, but in this case, we have the slope. From the slope, we discover that we are able to obtain our g. So our conclusion is that from this experiment, we have been able to obtain g, and our inference will be that whether g is equal to 10 whether it is 9 plus or 9.8, depending on what you obtain. You can now adduce reason. If your G falls short of 9.8, you may adduce reasons as to why it does so. If it is more than 9.8, you can also adduce reason and make deductions and inferences. Thank you very much.